All right, 20-1s. Here we go. We continue with Chapter 9, Inequalities. So today's lesson, as you can see, it's about two variable inequalities. The first lesson, we talked and looked at single variable inequalities, meaning we could have linear 2x plus 4 equals 7, and we just needed to solve for the single variable. Well, we also had quadratics, 3x squared plus 4x minus 8 equaled 0, single variable being x's only, and that was where we needed to find our x values and figure out, because it was inequalities, with inequalities, we needed to identify where our quadratic was less than 0. So in this case, we could have thought of it as a quadratic. This portion was less than 0. So only working with single x variables. Well, now that we're getting into two variable inequalities, we now have x's and y's. So y is going to be less than or equal to 4x minus 7, or y is greater than 3x squared plus 2x plus 1. Now we have x's and y's in each inequality. And because of that, we need x and y values, which is now putting us onto Cartesian grids. And we need to come up with not just an x value like we did single variable, we need to come up with x and y values that can be substituted in to suit the inequality. In this case, we would need an x value and the y value, so the left side is always greater than the right side. There's going to be multiple possibilities, but how do we come up with those? Well, it's applications of information we already have. So if we start with two variable linear inequalities, well, if we think linear, we're creating lines. This goes back to 10C using the slope-intercept equation. So when we had the equation y equals 3x plus 2, well, what did this mean? Well, our b value was 2. Remember, the b value is your y-intercept. We also have, in this case, an m value of 3. Well, remember, m is your slope, which is the rise over run. And if I have a whole number, I can always put it over 1. And if the slope is 3, or 3 over 1, we need to go up 3, right 1 to get to the next point. Up 3, right 1 to get to the next point. Or down 3, left 1. Down 3, left 1. So I can create the line. Let's see how good I am. It's not bad. Relatively straight. So there's our equation of y equals 3x plus 2. We were able to take an equation, two variables, linear, y equals mx plus b, and create a line. Well, now we're looking at taking that, but our equation now needs to become an inequality of some sort. Y is less than mx plus b, or y is greater than mx plus b. Our example, y is greater than 3x plus 2. It's not equal to anymore. How do we solve an inequality? Well, it's really not that complicated. It's just something you got to think about. So in this case, y is greater than 3x plus 2. Well, we had just graphed it. So I'll quickly do that again. And I regraph very quickly. And I end up with that same line that I had first time. So there's y equals 3x plus 2. But we want y to be greater than the 3x plus 2. Well, what that means we have to do is we need to shade the region that is greater than the 3x plus 2. So what's greater than that 3x plus 2? Well, here's the 3x plus 2 line that we created. We want the things greater than it. Greater means above. So all of these sections above 3x plus 2 is solutions. All of that shaded region, if you pick a point in that shaded region, -7 and 4. Well, -7, 4 is in the shaded region. Well, that means -7, 4 should be a solution for the inequality. That's all there is to variable linear inequalities. We don't have just the line anymore. We need a whole bunch of points greater than that line. That's what we're looking at doing. So let's take a look at page 14 before we start doing a whole bunch of calculating. What do we do to come up with the inequality? Well, here we have the sketch of a two-variable linear inequality. Well, the first thing we need to do is we need to figure out what the equation of the line is. Well, to come up with the equation of a line, going back to the 10C course, y is mx plus b, we need to know what's the y-intercept. Well, we can see on this graph the y-intercept is -3. So our b value is -3. The second part is we need the slope. Well, to get a slope, if you recall, we want to find 2 points of intersection. Any 2 points of distinct intersection, there's 2 there that I'm going to work with, and get the slope. What's the rise? 1, 2, 3. We have a rise of 3 positive, and then we have 1, 2, a run of 3. So our slope in this case is rise of 3, run of 3, so our slope is 1. So once I have slope and intercept, y equals, our slope is 1, x plus the y-intercept of -3, which I can write as subtract 3. So we have the equation of the line, y equals x minus 3. But now we need the inequality. So I still have the y, I still have x minus 3, but now, instead of an equal sign, we need an inequality sign. Well, given our line, what's shaded? Everything above our line is shaded. So we want all the y's that are greater than x minus 3. The last bit that we'll talk some more about, if you take a look at that original line, it's a solid line. We can see that our line that was created is a solid line. So that means we want the line to be part of our solution. So there's our inequality. The equation of the line that we have, and then the shaded part tells us what our inequality is. It was above, so we wanted the y values greater than x minus 3. Now, how does this work in being our solution? Well, this is where we can verify. Because like I said a couple minutes ago, any point within this shaded region, and I mean it extends for technically forever, any point inside that shaded region is a potential solution. So what we can do is we pick a point from within that solution, any point. Well, what's a nice easy one to work with? Well, 0, 0. 0, 0 is a really nice easy point to verify. So y is greater than or equal to x minus 3. We think 0, 0 is a solution. So we can substitute in and check. If y is 0, we think it should be greater than or equal to x, which is 0 minus 3. Solve the left side, solve the right side. Is 0 greater than or equal to negative 3? It is. 0 is bigger than. So the left side is greater than or equal to negative 3. So 0, 0 is a solution, which it should be because it's within the shaded region. Pick another point. Well, let's try going to point 7, 10. 7, 10 is in the shaded region. So 7, 10 should also work. So if I check with 7, 10, well, y is 10, and that should be greater than or equal to x, which we're calling 7 minus 3. There's our x and y substituted in. Left side is 10, and the right side is 7 minus 3, which is 4. Is 10 greater than or equal to 4? Absolutely. So yeah, 7, 10 is another solution for the inequality because it's in the shaded region. Well, the last verification, let's pick a point that isn't part of our shaded region. So let's just go to 5, negative 2. There's point 5, negative 2. Now 5, negative 2 isn't part of our solution. So if I were to plug something that isn't correct into our inequality, something that's not a solution shouldn't work. Let's see what happens. We say that y is negative 2, greater than or equal to x, which we're calling 5 in this case. 5 minus 3 is negative 2 greater than or equal to 2. Well, no, that's not true. The left side is not greater than or equal to the right side. It's not true. But it shouldn't have been true because that's a point that's not in our solution area. So all two variable inequalities are doing, we're making the graph, but then we're identifying all the multiple possible points, x and y, from the Cartesian grid that should satisfy it. That's what linear inequalities are. So we want an equation for the graph. We then want to put in an appropriate inequality sign based on what's shaded, above or below. We need a greater than or a greater than equal to sign if it's shaded above the line. We need a less than or less than equal to if it's shaded below the line. Now here's the key point. The hardest part about this that I always forget about is whether we need the equal to or not. If the graph is a solid line, that means we're using greater than equal to or less than equal to. It means we want it. So the example on the screen, that's a solid line. So we had y greater than equal to x minus 3. If the graph was a dotted line, that would be saying don't include, just less than equal to. So if I have this exact same graph, but my line, initial line, wasn't a solid but a dotted, but we still had shaded above, we would be saying y is greater than, because we're shading above but not equal to. So y is greater than x minus 3, and the dotted component of the line is saying doesn't equal. So that's how you show inequalities with two variables. So page 15. Let's create the inequality for that bottom right question. We need the inequality for the graph, and then we need to verify as well. So the first thing is we need the equation. So let's come up with the equation for the line just as an equation with an equal sign. Well, what do we need? We need to know what's our y-intercept. We can see the y-intercept is at 1. What's the slope in this case? Well, pick 2 points of distinct intersection. So we have a rise of 2 and a run of 1. So we have a slope of 2 over 1, or just 2. So there's what we need for the equation. Y is equal to 2x plus 1. However, we now, after we have the equation, need to convert to the inequality or inequation based on the shading. And again, we've shaded above, so it has to be a greater than sign. But the second part is it's a dotted graph. So we don't want it equal to. So we still have the y, the 2x plus 1, but it's no longer an equal sign. That now converts. We want y to be greater than 2x plus 1. Not equal to. Y equal to means it would have been a solid line because we would want it to include it. So the last part, let's verify. Let's pick a point and see if we're correct. Well, I'm going to pick a point that's kind of close to my line. So that's point -1, 1. Now, -1, 1 is in the correct shaded region. So my verification, if I check with -1, 1, y is 1, that should be greater than 2 times -1 plus 1. My left side is 1. -2 plus 1 is -1. Is 1 greater than -1? Absolutely. My inequality, left side is greater than right side, is true when I use -1, 1. So I at least pick one point that's correct. I'm on the right track. I'm going to trust my solution. Next page, page 16. Give that one a try. Pause the video. Try to come up with the inequality there. See what you get. And then turn it back on and I'll walk through it. So here we go. First thing, I need my equation. Y is equal to, I have a y-intercept or b value of -2, and we have a slope. There's one point, and another point is here. So my rise is -2 down and a run of 1. We do see the line is going down, so it makes sense. 2 down, 1 to the right is a slope of -2. So we have -2x minus 2. There's the equation, but now we need to convert it to the inequation. Well, what have we shaded? If I'm on, first of all, it's a solid line. Note that the line is solid, so we know we're going to be equal to, and we have shaded above the line. So y is greater than or equal to -2x minus 2. Well, let's pick a point and verify. Always helps to do a quick check to see if you're on the right track. Look at that, 0, 0 is a possible. 0, 0 is nice to verify with because it's a nice easy value. So if I verify with 0, 0, y is 0, and that should be greater than or equal to -2 times x, which is 0 in this case, minus 2. 0 is greater than or equal to 0 minus 2, which is -2. 0 is greater than -2. That's true. My left side is greater than or equal to my right side. So 0, 0 makes sense. So I trust that linear inequality. There you go. All right, the second part to this is graphing the inequality. So instead of creating the inequality, we can graph it. Well, it's not a lot different than what we were talking about. It's just the other direction. So the first thing we have to do is we have to graph the line using y equals mx plus b. Remember, when you're creating that, do you use a solid or a dashed line? So if I want to graph this, My y-intercept is 3. My slope is negative 2 over 1. So my y-intercept is 3. And my slope, negative 2, 1, would be 2 down, 1 to the right, 2 down, 1 to the right, 2 down, 1 to the right, or 2 up, 1 to the left. So create your line. Doesn't have to be perfect. But when I'm creating the line, do I want solid or dashed? Y is less than, doesn't equal, so that means my line needs to be a dashed line because we don't want to include it. So we want the dashed line, and now we check the inequality and shade the appropriate portion. Y is less than negative 2x, and if we're less than, we shade below. So I would then quickly shade everything underneath, and there's the graph of y less than negative 2x plus 3. Everything that's shaded could be a solution. Doesn't always ask for it, but it always helps. Pick a test point. Pick a nice, simple test point or a difficult test point, whatever you want. I'm going to go negative 2, 4. That negative 2, 4 is inside the shaded, so it should make the inequality true. So to verify, we say that y is 4, and that should be less than negative 2 times x. Our x is negative 2 in this case, plus 3. 4 plus 3 gives us 7. Is 4 less than 7? Absolutely. 4 is less, so my left side is less than my right side using negative 2, 4. So at least I have a point within the right region, so I have to hopefully at this point trust what I've created. Graph the line. Make sure you use the appropriate solid or dashed line. Shade appropriately based on a greater than or a less than symbol, and then verify just to make sure. Page 15, give it a try. 10x minus 5y is greater than 0. Pause the video, give it a try, see what you come up with. All right, so this one might argue that it's a little trickier because, again, we want to graph y equals mx plus b. We have to do a little manipulating. So in this case, I'll take 10x minus 5y greater than 0, subtract 10x from both sides. Negative 5y is greater than negative 10x. Now I need to divide by negative 5. So be careful. So y is now 2x, but my greater than sign, remember, you need to reciprocate, or sorry, not reciprocate, but flip the inequality because you divided both sides by a negative. So my greater than now becomes a less than, and we really want to graph y less than 2x. Don't forget to flip because we divided both sides by a negative. The rule of inequality algebra. So in this case, y is less than 2x. If I were to graph y equals 2x plus, what's my b value? Well, technically it's a 0, so that makes it simple. My slope is 2 over 1. So up 2, 1 to the right, up 2, 1 to the right, and so on. Down 2, 1 to the left, down 2, 1 to the left. Straight edge. We can graph that. Now, this I did say is where I always kind of make mistakes. I'm so used, I want to connect those points, but have I graphed this correctly? I haven't because we're less than. We want to graph y less than 2x. So I don't want to erase all my points. My graph will be in red. Because it's just less than, I need a dotted line in this case. So my graph has to be a dotted line or it's wrong. And now, what do I want? I want y less than 2x. So less than means everything below. So this is the region of my solutions. Everything below my line y less than 2x. I like to do a quick verification because I'm a math geek. Pick a point, same as always. So in this case, I'll pick the point 2, 1 to verify with. Always verify in the original. Don't verify in your work. Verify the original question. That's where it should work. So we had 10x minus 5y should be greater than 0, and we're going to verify with 2, 1. So when I plug that in, 10 times x, which is 2, subtract 5 times y, and y is 1. That should be greater than 0. 20 minus 5, 15. 15 is greater than 0. That holds up. So 2, 1 is a solution, which it should be because it's in the appropriate region. Well, I hope then I can trust what I've done. 2 variable linear inequalities. All right, so now skip to page 21. We aren't going to do anything different when we look at 2 variable quadratic inequalities. I'll be honest with you, it's the exact same process. On our Cartesian grid, we're going to come up with a parabola, and I'm just making this up. It's some parabola. So let's say we have y is equal to an x squared plus an bx, ax squared plus bx plus c. But in this case, solid line, what does that tell us the way I graphed it? Well, I would have to, instead of having equals, I would have to say it's going to have an equal because it's a solid line. And then it depends upon what's shaded. I could shade everything around the parabola. Everything around the parabola, that means it's all the points, technically, if I extended this forever, those are all the points under the parabola. So in this case, I would have y is less than or equal to, because it was solid, ax squared plus bx plus c, whatever my equation was. Similarly, if I had a different one, let's say I had it over here, a parabola. Whoops, let's do this. Just so again, 2 variable quadratic, if I had this parabola and I had it shaded here. Well, for that one, what we'd be looking at, again, for the equation, it would be a y equals ax squared plus bx plus c. But if I wanted the inequality, well, in this case, it's a dotted line. So that means I don't have equal at all. It's greater than or less than. And what's been shaded? Well, in this case, it's everything above the parabola that's been shaded. So we would have to say that y is greater than ax squared plus bx plus c for that situation, but not equal to because it's a dotted line. So create the graph. Now it's a parabola instead of a line. Shade based on the inequality. Again, greater than is because it's shaded above. It'll be a less than if it's shaded below. And we can always pick a point and verify. So let's take a look. Now the biggest problem with quadratics, linears are easy to graph. You need your intercept, you need your slope. We graphed equations back in chapter 3. Lots of work. That's the drawback to this. The work isn't tough with the inequalities, it's all about the solving. So if we take a look at page 21, and we want to do the work for y is greater than or equal to negative 2x squared plus 8. Well, y is equal to negative 2x squared plus 8. If I want to graph this, and I'll be honest with you, on an assessment, we wouldn't ask you to do a ton of this graphing. But let's just review. So if I wanted to graph this, there's all kinds of ways to graph. one thing you could do is get your x-intercepts. X-intercepts can help to graph. So x-intercepts is when y is equal to 0. So 0, negative 2x squared plus 8. Well, what would I do to get my x-intercepts in this case? Well, what I would do is I would move the 8 over. Negative 8 equals negative 2x squared. That's gone. Divide by negative 2. So 4 is equal to x squared. Get x by itself, you square root. So remember, when we square root, it's the positive or the negative. So the square root of 4 is positive or negative 2. So there's our two x-intercepts, 2, 0 and negative 2, 0. So there's some information that I could use to do my graph. The other possibility to do my graph is get the y-intercept, because the y-intercept is a nice value as well. Y-intercept is when x is 0. So if I take that same equation and I put x equal to 0, y equals negative 2 times 0 squared plus 8. Well, 0 squared is 0. Negative 2 times 0 is 0. 0 plus 8. My y-intercept is at 0, 8. Now, technically, that should be enough information to do a decent job of the graph. Last possibility, if you really want, another possibility is to get the vertex from vertex form, because we've worked with that a lot this year that maybe you've gotten so good at it, you want to keep going. So in that case, you want to factor out, so x squared is by itself. You would have negative 2 x squared plus, there isn't an x value, and you have the plus 8. So at that point, when we're doing this to get the vertex form, well, I'm not going to actually factor that out. We're just left with negative 2 x squared plus 8. So where's our vertex? Our vertex for this, p-value, there is no p-value. So it's just going to be 0, and our q value is at 8. So look at that. Our vertex and our y-intercept are actually the same in this case. So there's all kinds of things we can do. We know, like we just said, intercepts are at 2 and negative 2. Our y-intercept was at 0, 8, not 0, 7, but 0, 8. There's enough information to do a nice sketch of our parabola. But now, once we've graphed, now we need to check the inequality sign and shade appropriately. Step 2. We want y greater than or equal to, well, I did a solid line, which is good because it's equal to, and y is greater than. Greater than means everything above. So all of these points above are part of the solution. So if I extended these down a little bit, all this area here is part of the solution. Those are the y values greater than or equal to negative 2x squared plus 8. Verify, pick a point. Well, just because it's a unique point, I'm going to pick point 010 because it's close to the parabola, but not. So let's check with that. We think y is 10 greater than or equal to negative 2, 0 squared plus 8. We have 10 on the left. 0 squared is 0 times 2 is 0 plus 8 gives us 8. Is 10 greater than or equal to 8? Absolutely. So 0, 10 is a good verification point. It should work because it's in the region. So honestly, graphing the parabola is the tricky part here. Shading greater than, less than shouldn't be too difficult. Now, page 22. Page 22, what we're looking at is actually, if you take a look at the example there, Page 22 at the bottom, y is less than or equal to negative x squared plus 2x plus 4. It actually has the graph. My question is the graph correct? Well, let's do a quick check to see if the graph is correct. Well, if y is less than or equal to negative x squared plus 2x plus 4, I'm going to have to do some math to get the important points. So we have y is equal to negative x squared plus 2x plus 4. I'm going to get the x-intercepts. Y is equal to 0. So now I'm going to solve so I can get my x-intercepts. So x-intercepts, at this point, I need to factor if I can, but the question is, can you factor this? I'm not positive that you can factor it, but you can't. It's that simple. So what do we need? Quadratic formula. B, negative b, plus or minus the square root b squared minus 4 times a, which is negative 1, times c, which is 4, all over 2 times a. So in this case, x works out to be negative 2 plus or minus, this works out to be root 20 over negative 2. Now we're trying to get x-intercepts on a graph. I can now just plug this into my calculator because I just need the x-intercepts. Negative 2 plus root 20 divided by negative 2, and negative 2 minus root 20 divided by negative 2. When I do those calculations, we end up with, technically here we get 1 minus root 5. But honestly, because we're graphing it, we can just go to a decimal value. There's nothing wrong with that. Because we're graphing, we can come up with the estimates, and this works out to be an x value of negative 1.2324, my x-intercept. This one, if you simplified, is 1 plus root 5, and 1 plus root 5. When you, again, just plug that into the calculator because we're going to graph it, is an x value of 3.24. Y is 0. So I can go back to my graph now. I have negative 1.24. Whoops, negative is to the left, not to the right. Negative 1.24. And then I have positive 3.24. So there's my x-intercepts. What else can you get? Well, here's what's nice. Is the other one that's nice is the y-intercept when x is 0. If I just want to do a quick graph, y-intercept, x is 0. Well, these are all zeros, so y is equal to 4. So we have 0, 4 is the y-intercept. So the y-intercept is at 0, 4. Symmetry, we talked symmetry, we know, well, these are about 4 apart. So our symmetry, we're going to be another point around there. So our parabola would look something similar to that. Do we have that? Absolutely. Negative 1.24, 3.24. Our vertex is close. Absolutely. The graph that's there, we came up with the same graph and we were able to graph it. Now though, let's finish it off. Y is less than or equal to. So I graphed with a solid line, which was good. Y is less than. So all of the points less or under are the solution. So everything under is the solution. So what was given, we have totally verified by graphing the parabola and then shading. You can do a verification. We've done a lot of them. Again, what's nice with verification here? Well, we get 0.00s in there. So quick verification. 0 is less than or equal to 0. 2 times 0 is 0. Is 0 less than or equal to 4? That's true, and it should be because 0, 0 is part of our solution. So the graphing can be tricky. The last one is to create the inequality. Well, creating the equation for a parabola, one more time, it's tricky. This is review stuff, but this is where the complication comes in. So create the equation for the parabola. Well, to create the equation, remember we find the x's. What are our zero values, our roots? Well, we have x equal to -2, and we have x equal to 3. And so when x equals -2 and x equals 3, what we want to do at that point is we know that if x is -2, that's for the point x plus 2, and if x is 3, that's for x minus 3, and that should equal y. So now I can do FOIL x squared minus x minus 6 equals y. But I don't like the equals because we want an inequality. X squared minus x minus 6. What's been shaded? Everything above. So we know that y has to be greater than, because we want above our parabola, and it's a solid line, and the solid line tells us to make sure it's equal. So there's the inequality for this particular question. So a little bit different, but it's just a matter of shading because we need xy values for two variable inequalities. It's about the graph, and the portion that's shaded above or below gives us a whole bunch of xy values that will make the inequality true. There's your assignment. Again, please understand, on an assessment, if we give you easy things to graph, you should have that knowledge. On an assessment, we wouldn't give you big, ugly calculations with the quadratics. But if it's fairly straightforward ones, this is information we've covered this year in this course. So give that stuff a try. Reach out if you have questions. Have fun with it.